Hello student, welcome to Yourpedia education. This is our second lecture in physics. In first lecture, I discussed about all the fundamental laws of photoelectric effect, including both practical as well as ideal consideration. Fine. So in today's lecture, I will discuss some important terminology and MCQs questions as per the requirement of the exam from this concept photoelectric effect. And I will make sure I will discuss all different type of questions which have been asked till now in the exam. Fine. Now see, as per my survey and experience in previous year exam, examiner mostly focused either on the intensity, either on the photon flux, either on the stopping potential, either on the photoelectric current. Fine. Now see, next I wrote effect of frequency variations and effect of intensity variations. Questions are many. How photoelectric current will vary if the frequency of the incident light is varied? How photoelectric current will vary if the intensity of the incident light is varied? How stopping potential will vary with both? How maximum kinetic energy or fastest electron velocity will vary with frequency as well as the intensity? That all I will conclude here. Fine. Now see, and I will make sure whatever discussion I will have here, that is all as per the requirement of exam. Okay, so I will try to limit in the constraint of the exam requirement. Now see, before starting further, in previous lecture I discussed you EP. EP is the energy of photon which we represent student h nu. Fine. And I have told you one transformation, 1 electron volt is equal to 1.6 into 10 raised to power minus 19 joule. See, joule is unit of energy, electron volt is unit of energy. 1 electron volt usually you defined as the energy gained by an electron when it has been accelerated by a potential difference of 1 volt. That I will discuss in the electrostatics when I will teach electrostatics. Fine. But in quantum physics, mostly you deal the electron volt unit of energy. Okay. And I have told you in photoelectric equations, we have three energies. Energy of the ejected electron, which is maximum kinetic energy, and incident photon energy, and work function of the metal. Usually work function of the metal is defined in electron volt. So you can't use that. You are using the energy of the photon in joule and work function in electron volt. You need all the energy in the same unit and on the same scale. So many times students commit this mistake. They don't see the unit. They directly calculate EP, photon energy, by putting H and frequency relations. H they use directly of the Planck's constant in joule per second, and they get the wrong answer. So first of all, I will tell you people what will be energy of photon in electron volt. I have told you student, this H is Planck's constant and its value is numerically 6.6 into 10 raised to power minus 34 joule second. Fine. So if I want energy of photon in electron volt, I need to convert this joule into electron volt by using this transformation. So I can make H frequency in term of wavelength C upon lambda. I need to divide by this amount if I want to convert joule to electron volt. Fine. And this is an electronic charge, so I'm dividing here E. If I substitute H, C and electronic charge value, I will get calculation 12375 upon wavelength in angstrom. Keep in mind, and some typical approximated version, I can take 12400 upon lambda angstrom. In most of the textbook and most of the places you will find this value. Okay, it is up to you. You want to use exact, you want to use approximate. Now see student, if you want to calculate energy of photon in electron volt, then you can use this relation directly, but make sure that wavelength in this relation is in angstrom. If examiner has given in nanometer, micrometer, first convert into angstrom and then substitute that value here. Is it clear? So this is the first point where most of the students commit mistakes. Second point, to understand further, see student, today in introduction I will discuss some of the practical points because they are very important and necessary to understand the stopping potential concept. Without these practical consideration, you can't understand the stopping potential concept. You can't understand what will be effect of frequency variation. You can't understand what will be effect of intensity variation. So that is why I am concluding some point here. Fine. Next, I have told in the previous lecture that if kinetic energy is asked, what will be kinetic energy of ejected electron? Usually student, you use this relation, maximum kinetic energy is equal to h nu minus phi, right? So this is under ideal constant. This is under ideal constant. When you are not considering any losses in the collisions, you are assuming that all things are happening ideally. Okay. So definitely kinetic energy of the ejected electron will be maximum, and we can say this is corresponding to the energy of fastest ejected electron 1 by 2 mv max square. Is it clear? Now see, if I take practical consideration, then this kinetic energy will be less than equal to h nu minus phi. It means in this equation also maximum value is this one, which will be when we are assuming the ideal constant. So this is including practical constant also, including practical constant means losses in the collisions we are taking into consideration, which usually you don't. Okay, now see student, now every electron will suffer from different amount of loss in the collisions. We can't say all the electrons are suffering same amount of loss in the collisions. It means their energy after the losses in the collisions will be also different, means their kinetic energy will be different. It means student, their kinetic energy will be distributed between a range. Now tell me, what will be that maximum range? Maximum will be kinetic energy maximum, which you told how much? H nu minus phi. Now what will be minimum? 0, because we are talking about the kinetic energy of the ejected electron, that cannot be negative. So whatever electron ejected from the metal surface, their kinetic energy is distributed between this range if we consider practically the losses in the collisions. Is it clear? Fine. So what I can conclude from here? I can conclude from here that all ejected electron from metal surface may have different kinetic energy, distributed from 0 to Ke max. You can see on the scale. This is very important concept which will help you in the stopping potential understanding. Fine. Now third point. I have told you student in last lecture that according to Planck's explanation, a photon is an energy packet, fine, which if absorbed by the electron, it is fully absorbed, not partially. Means one photon cannot be absorbed by more than one electron. Ultimately means one photon, provided condition it carries energy greater than work function, can eject at most only one electron. So what I am writing here, during phenomena of photoelectric effect, one photon, provided its energy is greater than work function which is required for the emission of electron, one photon can eject at most only one electron. These are very important conclusions, student. Now see student, someone says, sir, I have told you effect of frequency variation. Sir, if I increase this frequency, then will the number of ejected electron increase? No, you can see directly from here. What will increase then? You can see here, this factor will increase. For a particular metal surface, this is constant, work function is constant, obviously your maximum kinetic energy will increase. It means if you are increasing the frequency of incident light, ultimately you are increasing the maximum kinetic energy of ejected electron. You can't say that by increasing the frequency of incident photon you can expect more number of ejected electron. No. Hopefully, right? So these are the three conclusions. Now fourth very important conclusion you can see here. Number of emitted photon or number of photon emitted by a source per second. For this student, first of all we need to assume a light source. We are having a light source. For example, we take a bulb, which you all are aware of, with power P. Fine. And I am assuming it is 100% efficient. Hopefully you know. It means all the energy is emitted in the form of the light, not in the form of heat and all. This is ideal conditions, which is practically not possible. So I am assuming ideal condition. You can see in some of the numerical, examiner says your light source is 80% efficient. It means it is converting only 80% of the input energy into light, 20% in the heat or other wastage. So that I will discuss in the numerical. Okay. Now, if this bulb is emitting light, definitely there will be some corresponding wavelength and frequency. If I assume the emitted light by this bulb have wavelength lambda or frequency nu, then what will be photon energy in this emitted light, EP? That will be simply h nu, we can write in term of wavelength hc upon lambda. But our constraint is number of emitted photon or number of photon emitted by source per second. Fine. Now see student, you know the power of this bulb is P. We can write power energy upon time. Now energy is emitted in the form of the photon. So if we assume N is the number of photon emitted and EP is the individual photon energy upon T. We can write this because whatever energy it has emitted in some particular time, that will be in the form of the photons. And this is the photon individual energy, and total energy will be number of photon multiplied by the photon individual energy. So what is N here? N is number of photon. N is number of photon. Right? Now see. Now can we define P is equal to small n EP. Now what is small n? Small n is capital N upon T. Number of photons per second. Number of photon emitted per second. So can we say number of photon emitted by the source will be its power upon energy of individual photon. Is it true? Hopefully clear. Here it is very simple discussion. Keep the terms very simple to you people. Don't try to complexicate the things. Okay, now see. We take one numerical. Now see student, question is light of 4 into 10 raised to power 14 Hertz is produced by a laser. Power emitted is 6 into 10 raised to power minus 3 watt. Power is given in watt. How many photons per second on an average are emitted by the source? Now you know number of photon per second emitted by the source is power upon photon energy. Now this is given in watt. So you don't need to calculate this photon energy in the electron volt. You can keep this in the joule, no issue. Hopefully you understand. Fine. So power is equal to how much? 6 into 10 raised to power minus 3 upon photon energy h nu. Substitute the value. What I will get? 6 into 10 raised to power minus 3 upon h is what? 6.6 into 10 raised to power minus 34 into frequency 4 into 10 raised to power 14. So approximately I will get somewhere around 2.2 into 10 raised to power 16 photon per second. You can check. So your A is the answer. Keep in mind student. Fine. Now see next. Now next is student intensity. We also call it energy flux. Fine. So it is defined as energy crossing normally per unit area per second, or you can say it is defined as energy crossing per unit area normally per second, is the same thing. So mathematically, if I write it, intensity represented by I is equal to energy E per unit area per second T. Now see student, whatever energy is crossing per unit area, that will be in the form of the photon. It means if I express in form of the photon, it will be n EP, number of photon, EP, individual photon energy, upon AT. So if I write it separately, sum like n upon AT multiplied by EP. Now tell me, what does this term represent? This term represents number of photon incident on a normal surface per second per unit area. Number of photon crossing normally per unit area per second. Means it will tell what is the number of photon per unit area per second required to carry this energy. If this is the energy crossing normally per unit area per second, definitely that is carried in the form of the photon. So there will be number of photon crossing that area per unit time. So this is that number. This we define, student, very important, photon flux. Phi n represented by photon flux. Keep in mind, photon flux, very important term. So it can be defined as number of photon incident on a normal surface per second per unit area to carry that energy. Which energy? This energy E. Is it clear? Or you can define number of photon crossing normally per unit area per second to carry this energy E. Is it right? Now see student, we can write intensity I is equal to phi n multiplied by EP. Means phi n photon flux can be written as hc upon lambda. Is it clear? Means photon flux phi n we can express in term of I lambda upon hc. Again, very important relation. Is it clear? Now, listen one more thing here. If I consider this terminology, what is this? Energy upon time, obviously power. So this intensity in other way we can express as power per unit area. Now very important point here is student, for a light emitted with frequency nu or wavelength lambda, how I can increase its intensity? How I can increase its intensity? See, one thing from here, it can be written as n h nu upon AT. Fine. So you can see intensity is also depending upon number of photon and frequency. This is very important. But I am asking for a light emitted with frequency. This one means I have kept frequency same. Frequency is now constant, fixed. How I can increase intensity? How I can increase intensity? Tell me, how I can increase intensity? Up arrow means increase. Obviously, by increasing, upper arrow means increasing photon flux. Number of photon per unit area per second. Is it clear, student? So there should be no confusion, because see student, when we are falling light on metal surface, we are falling light of fixed frequency. In photoelectric effect, so in photoelectric effect, if we are increasing intensity, our frequency is constant, means we are talking for a light of particular frequency. If we are talking for a particular frequency, then we need to increase photon flux, number of photon per unit area per second, only then your intensity will increase. Is it clear? Hopefully, right? Now let us conclude very important point. I told you earlier. Now we will see what will be effect of increasing frequency and what will be effect of increasing intensity of incident light keeping the frequency same, means for a particular frequency. Now two parameter till now. Till now I haven't discussed stopping potential. Till now I have discussed maximum kinetic energy of ejected electron and photoelectric current. What is photoelectric current? It is the current, time rate of change of charge which is ejected electron due to the light emissions. Fine. So more number of electrons are ejected, more will be the photoelectric current. Simple concept. More number of carriers available for conduction, more current there. Okay. Now student, come to effect of increasing frequency. We are increasing frequency. By increasing frequency, tell me what will happen. E is equal to h nu. Energy of the photon will increase. So I have told you h nu should be greater than phi. Then photo emission will occur. Keep in mind, photo emission will occur. I have told you. Fine. And I have told you in the assumption one photon is capable at most ejecting only one electron. So you are not increasing here number of photons per unit area per second that you are doing here. Here you are increasing only frequency. So you are increasing the photon energy. Means the number of ejected electron will be same as they were for the previous frequencies. Because increasing frequency doesn't increase the number of ejected electron. For that you need to fall more and more photon. But here you are not falling more and more photon, you are falling more energetic photon. You are not falling the more number of photon, instead you are falling some same number of photon but with more energy. Means you are increasing this one, more energetic photon, this will be large. Now this is constant property of material. If you are increasing this one, ultimately this will increase. It means if you are increasing the frequency, keeping photon flux constant, you are not increasing the number of photon per unit area per second, you are just increasing the frequency, means you are making photon more energetic. If photon is satisfying this condition, doesn't matter how much energetic it is capable of ejecting at most one electron. Means question of ejecting more electron is not here. Means photoelectric current will be same, not affected. Photoelectric current will be only affected if we are capable of increasing more number of ejected electron. That is not possible here. But if you are increasing the energy of photon, increasing frequency, then this number increases. This is constant. Property of material, this is constant. Ultimately, more energetic photon will increase the maximum kinetic energy of ejected electron. So you can say it will only affect what? It will affect maximum kinetic energy of ejected electron. It will not affect. It will remain independent. It will remain constant with variation of frequency, keeping your photon flux same. So hopefully this discussion is clear. Now come to this side. Now what we are doing, effect of increasing intensity, keeping frequency same. Now if you are keeping frequency same, provided h nu is greater than phi. Okay. Now you are keeping this energy same, but you are increasing the number of packet having this energy. If you are keeping this energy same, energy of the photon is same. Energy of photon is same here. Energy of packet is same. But photons with this energy are increased. Photon number is increased. Photon number is increased. If energy of photon is same, this factor is same, means kinetic energy maximum of ejected electron, which is h nu minus phi, this is identical. So this will be same. This is independent of intensity, nothing concerned with intensity. So this will be same. This will be same. Means if you are increasing the intensity by keeping frequency same, how you can do that? How you can do that? How you can increase intensity by keeping the frequency same? Tell me. By increasing the photon flux, which I discussed in the previous slide. Number of photon per unit area per second you are increasing at fixed frequency, means you are increasing the intensity, means it remains same. We can say if intensity increases at a particular frequency, kinetic energy maximum of ejected electron will be same, not affected. Will be same, not affected. It means this will be same. But what about photoelectric current? But what about photoelectric current? What about photoelectric current? Obviously now I have discussed much about this topic. This will increase. This will increase. Why it will increase? Why it will increase? Up arrow means increment, because if you are falling more number of photon, you can see you are increasing the photon flux. More number of electron will be ejected, more number of carriers are available for current. It means photoelectric current will increase. This is current due to ejected number. This is current carried due to injected carrier or ejected carrier. Ejected carrier or ejected electron from the metal surface, or photo emitted electron from the metal surface. So more number of photon you will fall, more number of electron will eject, and more will be the photoelectric current. Hopefully clear. So this is very important discussion. Okay, now see next. Now this is one question. In this question, in photoelectric effect, listen carefully. The photoelectric current, which I just discussed, current because of the ejected electron, emitted electron by falling light on the metal surface. More number of electron will be emitted, more will be this current. I summarized in the last slide. Fine. First option, depend both on intensity and frequency of incident light. Both intensity and frequency of incident light. Does not depend on frequency but depend upon intensity of incident light. Increases when frequency of incident beam increases. Decreases when frequency of incident beam increases. So देखो C और D तो आप हटा ही दीजिए. मैंने आपको बताया है, I have told you already that increasing frequency doesn't increases the number of ejected electrons. So whenever there is question of frequency variation with reference to photoelectric current is constant with reference to frequency variations. Now come to A. Depend on both intensity and frequency of incident light. Not, because independent of frequency. So answer will be B. It depend on intensity of incident beam, not on the frequency. Why? Because I have told you photon flux, phi n, number of photon per unit area per second. More is this number, more number of electrons are ejected. More electrons are ejected, and more will be the photoelectric current. So it only depend on incident beam intensity of a particular frequency, not on that frequency. Keep in mind. Is it clear? Fine. Now see next question. Now next question is also very conceptual question. I have told in the first lecture, the work function, which is the minimum amount of energy required to eject an electron, it acts as a barrier. We need to overcome this barrier if want ejection of electron. Fine, I have defined in the first lecture. The work function for the photoelectric effect, option A, is different for different metal. Option B, same for all metal. Depend on the intensity of incident light, depend on the frequency of incident light. I have told you student in first lecture, work function is the property of material. It is not dependent on what we are applying externally. Externally we need to apply at least this amount of energy. So these C option and D option are wrong. They are property of material. They are not property of whatever we are incidenting on the metal surface. As per this work function, we need to meet our requirement. Fine. Is same for all metal? No. For aluminium it is 4.3 electron volt. For copper it is 4.7 electron volt almost. So it is not same for all metal. Means it is different for different metal. Fine. So answer is A. Reason, you all know that work function depend on the electronegativity. The least electronegative, most electropositive metal would let go of its valence electron very easily as compared to those metal with higher value of electronegativity. So that is very wide detail. I don't want to get into detail. I have already told you earlier that it is a property of material and it will be different for different metal. Fine. Now see next question. Now next question, you can see student, very good question. Einstein equations, photoelectric equations states that, which incident photon energy, work function and kinetic energy of ejected electron. I have told you symbol work function phi, and instead of that he is using W naught, so no confusion here. Fine. Now if I reframe this equation, Ek is equal to incident photon energy minus work function, which ultimately is equal to the kinetic energy maximum kinetic energy of the emitted electrons. Fine, which is ideal conditions. So option A, kinetic energy of all emitted electron? No. Option B, mean kinetic energy of emitted electron. I have told you practically kinetic energy is less than equal to this number. If all emitted electron have different kinetic energy, he is saying, is this the mean of that? No, it is not the mean of that. Fine. Maximum kinetic energy of emitted electron, yes, it represents the maximum kinetic energy of the emitted electron. What can be the maximum kinetic energy of ejected electron? That is this Ek. Fine, it means C is right answer, D is wrong answer. Minimum kinetic energy of emitted electron, no. I have told you whatever electron you have ejected, practically their kinetic energy is distributed between 0 and maximum, Ke max. Fine. Because when electrons is ejected, they suffer some loss of energy in collisions, and that is different for different electron. I have told in the basic assumptions. Okay, so these are the questions, student, which are framed on the practical consideration. So don't get confused with W naught. It is the alternate symbol used for the work function. So what will be right answer? Maximum kinetic energy of the emitted electron. Is it clear? Fine. Now see next problem. See, next question is, student, how many photon per second does 1 watt bulb emit if its efficiency is 20%? Means it is only 20% efficient and wavelength of the emitted light is 400 nanometer. So I have told you, student, when I discuss this number of emitted photon per second, at that time I assume the bulb which is 100% efficient. But now here is 20% efficient. It means clearly first take the efficiency. I need to check how much energy per second it is emitting in the form of the light. So out of 1 watt, 1 joule per second, out of that only 20% per second it is emitting in the form of the light. So efficiency means output power. Output power divided by input power. So I can write 20 upon 100. So what will be output power and input power? It is taking 1 watt. The rating is 1 watt. So this power will be 1 by 5 watt. Is it clear? As you can say, out of 1 watt, only 20% it is emitting in the form of light. Efficiency is 20%, means 1 by 5. Is it clear? Now see, I have told you what is the number of photon emitted by the light source per second. That is equal to power. Which power? Which is emitting in the form of the light. That is 1 by 5 watt, not 1 watt, because it was only 20% efficient. Upon EP. If you remember, EP is the photon energy. I can also write is P lambda upon Hc. In what wavelength of the light it is emitted? 400 nanometer. So substituting the value, and number of photon emitted per second will be how much? Tell me, student. 400 into 10 raised to power minus 9 upon 6.6 into 10 raised to power minus 34 into 3 into 10 raised to power 8 into 5. Why 5? This P is 1 by 5. If you calculate this number, this will be somewhere, it will be somewhere 4 into 10 raised to power 17. So keep in mind, student, when efficiency of the light source is given, light source is bulb. In my discussion previously, when I was discussing number of photon emitted per second, at that time I assume 100% efficient. That is why I utilize directly P, its power. But now efficiency is 20%, means whatever it is power, that out of that 20% it is emitting in the form of the light. So from using efficiency is output of any device divided by input. Input power is 1 watt, then output corresponding in the form of the light what it is giving, that is 1 by 5, because it is 20% efficiency. Fine. And by using the relations of number of photon emitted per second, I can directly calculate. So these are the type of the question which were asked in the exams, right? Now see, student, we are having this question. Next question: let Nr and Nb be the respectively number of photon emitted by red bulb and blue bulb of equal power in a given time. Fine. We know wavelength for red is greater as compared to wavelength for blue. Fine. If we calculate photon energy for different light is h nu, or in term of wavelength Sc upon lambda. So we have been asked with that whether the number of photon in both case will be same or different. If different, which will be greater, which will be lesser. I have told you, student, number of photon emitted by light source per second is small n is equal to power upon energy of photon, right? So it can be represented in term of lambda, hc lambda. Now you see this entire is constant and this is also constant because it is given that equal power. This is only the directional word given. You need to proceed according to this direction. Fine. So we can say n is directly proportional to lambda. So if lambda r is greater as compared to lambda blue, then nr should be greater than n blue. Fine. You can directly think of like this, if they are having equal power, then in a given time they are emitting the same energy, and the photon in case of the blue and red both will be of different energy. If you want to emit number of packets, and we wanted that those packets are transmitted such that they carry the same energy, but each packet weight is different, then the number which we need to send to balance that energy, that will be obviously different. Fine. Energy of the photon in case of the blue will be greater as compared to energy of the photon in case of the red. So it means we need more number of photon in red to balance that energy. Is it clear? So answer is concluding the same. So number of photon in red is greater as compared to blue. Now see next question. Next question, student, you can think the work function for sodium and copper is 2 electron volt and 4 electron volt. Find which of them is suitable for photocell with 4000 angstrom light. First of all, you must know what is photocell. Photocell is a device which converts light energy into electrical energy. Fine. It works on the principle of photoelectric emissions. Means I need to select metal out of sodium and copper such that photoelectric emission occur. Fine. So if I write the condition in term of wavelength, lambda should be lambda threshold for the occurrence of the photoelectric emission, or at least equal to threshold, right? And inverse for the frequency. Now listen, we are having a light of wavelength 4000 angstrom. Means I need to check whether 4000 angstrom, is it clear, is less than equal to lambda threshold of sodium, or whether 4000 angstrom is less than equal to lambda threshold of copper. Whichever out of these two, either both of these, if they satisfied photoelectric emission condition, that will be the suitable material. Fine. Now student, first we will calculate lambda threshold for sodium. How we calculate lambda threshold for sodium? It can be written as Hc upon work function of sodium. Since this is provided in term of what? Electron volt, I can use the same relation of which I use for the photon energy in electron volt, because symbol doesn't matter, ultimately it is the energy. So I can write here that student 12375 upon 2 electron volt for sodium. If I am writing this relation, then this wavelength should be in angstrom. Hopefully you remember relation, energy is equal to exact 12375 upon lambda angstrom. I am using the same relation. See, doesn't matter this is work function, but it is type of energy. Is it clear? So this value comes about for sodium 6187.5 angstrom. If I calculate same threshold for copper in angstrom, that will be equal to 12375 upon 4 electron volt, which will be somewhere down 3093.75 angstrom. You can use this or you can use the 12400, doesn't matter, only slight deviation will be there. Fine. Now see student, now tell me, this condition hold or this condition hold? Now if I check this, 4000 angstrom less than equal to for sodium 61875 angstrom, means see, this is the longest wavelength where photoelectric emission is possible. If this is the largest there is possible, then obviously here is possible, means this condition is satisfied. For second, we write 4000 angstrom less than equal to 3093.75 angstrom. This doesn't hold. Fine, because I have told you for working as a photocell, principle is photoelectric emission. So I need to select that threshold wavelength which satisfied these conditions corresponding to this wavelength of light. So tell me which is satisfying. Obviously sodium is satisfying, obviously this is satisfying the result. Fine, this equality I just use for the least, you can remove it over here. Fine, is it clear? Obviously this 4000 is less than 6187.5 angstrom. It is coming in the range. It means photoelectric emission is possible if I use the sodium. So answer is